Okay, looks like we're recording now, and go ahead and share my screen and we'll get going. All right, everybody seeing the slides?
Yep, I can see them.
All right, excellent. So, if you were in Monday's session, welcome back. And if you weren't in Monday's session, well, welcome for the first time. So, just some general thoughts to start out with. My general approach here, I mean that is what you're getting, but such as it is. But my general approach is that learning about electromagnetics is not about memorizing facts, figures, and so on. It's not about black magic with pointy wizard hats, magic wands, and all that sort of thing. But what it is about is learning a whole way of thinking about things and solving problems, and learning the language to effectively communicate effectively with other EMC professionals. I mean, any discipline basically has its nomenclature and essentially it a language. And that's part of what I'm trying to do here is to, to give you or teach you EMC literacy so you can communicate effectively with other EMC professionals. If you're using bad nomenclature, people will not understand what you're talking about, or worse, misunderstand it and think you're talking about something different. So, it's important to be precise about what we mean. An example I like to give, I've actually used it on charts and other presentations, but a town just a little bit to the east, about halfway between Goddard and Annapolis, spelled Bowie. When you all moved to the area, at least those of you like me who are transplants, what did you call it? Don't be bashful, I did too. You called it Bowie. I know I did. And it took maybe a few picoseconds before the locals made it very clear, no, it is not Bowie, it's Bowie. And it's the same with any discipline, engineering discipline or anything else. There is a nomenclature, there is a language for communicating effectively. You do not get to come in and move to the area and then declare that it's called Bowie. It is Bowie. So just say that, because people will keep correcting you until you get it right. And then it's also about providing a framework on which to build your ongoing knowledge and experience base. So there's not too much of a secret here. I'm certainly not making too much of a secret that I'm planning for retirement. And, I make the very reason I'm doing this is to pass along what I know so that people can continue doing this stuff, I hope correctly and properly, once I get on my bicycle and ride off into the sunset, whenever that might be. So anything like this is a continuous process, right? You don't just get to a point where, okay, I know everything there is to know about EMI. That's actually what I love about my job, is there's always something new to learn. This trip that I'm going to go on, I'm probably not at liberty to say much about what it is, but so I'm not. But it promises to be a new and interesting experience. So even on the cusp of retirement, I still have opportunities to learn new things. But the point is, uh, you know, I'm not giving you a bunch of stuff to just say, okay, now I know all there is to know. I'm kind of teaching you a way to think about it so that you can continue to educate yourself and just keep getting better at it. Hope that helps. And it's all about the laws of physics. So let's get on with it. Some terminology. I think many of you have seen this before, but uh, so getting right into some nomenclature and language. Electromagnetic interference, or EMI, is the phenomenon in which one component subsystem interferes with the proper operation of another subsystem due to the propagation of electromagnetic energy. Electromagnetic compatibility, or EMC, is the discipline of ensuring that electronic components or subsystems function together in the resulting electromagnetic environment. These terms tend to get lazily and sloppily interchanged. I'm as guilty as anybody, but they're clearly related, but they are distinct. So the way to think about it is we control EMI in order to achieve EMC. right? You're controlling interference so that you have compatibility. More terminology here. To have an EMI problem, you must have some culprit or aggressor on a component or subsystem that is an emitter of electromagnetic energy. Yes, I'm fully aware at some point I should bring my cultural references up to date, but this is what I got here. Then you must have a victim or components or subsystem that is susceptible to electromagnetic energy. And you must have a coupling mechanism, which is the process by which the energy from the culprit gets to the victim and causes interference. So in order to have an EMI problem, you have to have all three of these things. So, culprit, coupling mechanism, victim. To fix it, you need to address at least one of them. It's pretty basic stuff, but it really all comes back to these three things and how they relate to each other. So EMI testing is best performed at the component or unit level, and what that generally means is box level, but I'll talk more about box level testing here presently. That's actually going to be kind of the crux of what we're doing. But component or unit level to address problems before integrating onto the platform. Emissions tests are designed to, as the name implies, to assess emissions from potential culprits or aggressors, and susceptibility tests are designed to assess susceptibility of victims. And our primary coupling mechanisms are conducted, radiated, and crosstalk, which is kind of in a gray area between conducted and radiated. And, if you attended any of my fundamentals sessions where we talk about conducted and radiated issues, they're really one and the same. They're interrelated. If you've got a radiated problem, you've got a conducted problem somewhere. Radiation comes from uncontrolled currents. So these subdivisions are a bit artificial, but they at least help us categorize, when it's dominated by radiator, when it's dominated by conducted. Okay, so typical culprits and victims on spacecraft, there's no shortage of them. Typical culprits are radio transmitters, switching power converters. That's really one of our bigger ones. Fortunately, just our power group at Goddard, who I at least when I'm in the office, I'm in the same building as our power group in Building 20, and they have really done a wonderful job over the last several years with our in-house programs, basically taking care of this, that we don't really have significant conducted emissions or susceptibility problems with their in-house designs, because they have done a monumental job of addressing those issues. But when we get to some specific demonstrations in the lab, when we start with conducted emissions, I hope next week, if I'm back from travel, my example EUT, equipment under test, is a power converter that the power group let me use for this purpose. So you'll see how noisy those things can be. You also have motors, cryocoolers, high-speed digital electronics. The common theme here is high current or high-speed switching current. So for high-speed digital electronics, you're not necessarily talking about high magnitude current, but you're talking about it switching very fast. So that DIDT is really what gets you. And victims, radio receivers, detectors, sensors, low-level analog electronics, and many more. Clearly not an exhaustive list, but some examples. So why are standardized test methods important? Well, for emissions test methods, proper measurement techniques will ensure accurate and repeatable results, and that is very desirable for fix or no fix decisions. Right? If you're recommending that something needs to be fixed, you want to be able to stand by your test results and know that you did them correctly. Or if you're saying that, the other way around too, if you're saying that it's okay, that you passed the test, you want to be able to stand by those results too. And then for susceptibility test methods, proper test methods ensure accurate, repeatable, and controlled signal injection levels. That minimizes the risk to hardware. Any susceptibility test is inherently risky, right? You are stressing the hardware by design, but you want to, by design, control the signal that you're injecting so that you're not putting the hardware at risk, or they say you're minimizing the risk. Any susceptibility test is inherently risky, but you want to minimize that risk. And that's desirable for obvious reasons. You don't want to break hardware while you're doing an EMI test. And it has happened, and it's not pretty. Management doesn't really like that very much. And neither do the engineers who built the box that's being tested. So anyway, the running theme here is accuracy and repeatability. And also, I think is a very important point, credibility when you share your procedures and test reports with external organizations. And even internal organizations, really, because when you're going to management recommending that something be fixed, again, you need to stand by your results and know that they're accurate and repeatable. And another thing, I didn't put it on the chart, but the standardized test methods, another reason for them is you want to be able to go to any other test lab and run the same test and get the same results to within whatever slop factor you allow, right? But that's all part of accurate and repeatable, right? Any test lab should be able to run the test the same way and get the same result. So a little game here. Some of you probably have played this before, but here's this painting, and so name that painter. I'll give you the answer at the end when we're all done. But I came across this painting in a museum probably 30 years ago, and I was blown away at who painted this. And the other part of the quiz is guess the painter's age at the time of this work. And as with everything I do, there is a point, and I'll tell you what the point is when we're all done here. So, okay, so keep this painting in mind, and then I'll tell you who it was when we're all done. Okay, somebody has an open mic. If you can keep muted unless you're asking a question. We'll minimize background noise. Thank you. All right, so GEVs and EMC. Excuse me, just needed a sip of coffee. Baseline EMI requirements and test methods for Goddard programs are defined in the General Environmental Verification Standard for Goddard flight programs and projects. And that's GSFC standard 7000. So the G stands for general. It's sometimes it gets sloppily said Goddard Environmental Verification Standard. It's not. So there again, just be precise when you're quoting these standards. It is a Goddard standard, but the G stands for general. So Rev B was released in 2021. It is called a mandatory Goddard standard. We'll talk about what that means here coming up. And it's available at that NASA standards website there. You'll want to go to Center Standards because it is a Goddard specific standard. It is primarily based on Mil Standard 461, the latest Rev G. Requirements for the control of electromagnetic interference characteristics of subsystems and equipment from 2015. Now, Rev H update is in the works. I know some of the people who are on that committee. I am not personally on that committee, but I have submitted some comments to it that I think are going to be incorporated specifically to with regard to CS 101 testing. And I can share some of that when we get to that particular session in a few weeks. And then GEVS also references all of these documents here. So there's Mil Standard 461C, as well as 462 and 464. And then there's the space shuttle specification, what is called in the vernacular SLE triple ball 2. That's the only place I think I've ever actually heard it said as triple ball as opposed to 000, but that's how it's popularly said. And then that AIAA spec, I was actually on the committee for the most recent revision of that document, and that actually the most recent one is actually 2017. So I keep forgetting to update that. I think it was 2017, maybe 2018. So GEVS section 2.5 is organized as follows. 2.5.1 are the general requirements. That's what we're going to be talking about today. at least a representative sampling of them. But basically following the organization of Mill Standard 461, where the upfront section is facility requirements and things like that. This stuff we'll be talking about here coming right up. So 252 are the detailed requirements, the things that you know and love, like CE 101, CS 101, and so forth, when we get into like the specific test methods. And then 253 is the application guide that includes a discussion and rationale of general and detailed requirements. And that's also modeled after the application guide in the mill standard. So GEVS, the EMC section of GEVS, leverages Mill Standard 461 as much as possible, provides tailoring and additions as needed, and Mill Standard 461G should be kept handy as a companion document when you're using GEVS, because all through it, I mean, no mystery, I spearheaded the updates to the EMC section for Revs A and B, and so I call out, okay, do this, run, the whatever, the CE 101 test method per Mill Standard 461G with these tailoring guidelines. So you really should have Mill Standard 461G handy when you're using GEVS. So a counterexample is that SLE Triple Ball 2 document, the Space Shuttle EMI spec. That was written right around, I keep meaning to look it up, but late 90s or early 2000s, somewhere right around 2000, 2001 maybe. And 461E was the current version at the time. So it is essentially a rewritten version of Mill Standard 461E. I mean, I know some of the people who were involved in writing it, and they were also involved with the Mill Standard, so I'm sure they had access to a Word version of Mill Standard 461, and they just edited it for what was needed for the shuttle program. So it reads very much like Mill Standard 461, just tailored for the space shuttle. So it's a standalone document with the tailoring incorporated. So these are two different approaches. You can either write it as a standalone document, or you can just leverage the main document you're basing things off of. And I chose the levering option, because if I went with the standalone option, it would just be a very long document, or very one section of GEVS, right? The EMC section would have significantly increased in size, and I didn't think there was any reason to do that. I think it was just more time efficient to do it this way. So it was just a judgment call. But anyway, moving right along. Brief history of Mill Standard 461 and 462. I certainly love saying that the original release of those documents came out in the Summer of Love, 1967. And they started out as two separate documents. So Mill Standard 461 was all about requirements, so just the limits. Your emissions must be below this level, or you're susceptible. You must demonstrate you're not susceptible to this applied level, yada yada. But said nothing about how to do it. That's what was in Mill Standard 462, the test methods. So generally in 461, they will say using the CE 101 test method of Mill Standard 462. So you're meant to have them, both documents together. They're companion documents. 462 went to Notice 2 in May of 1970. That really is the dominant version that we used for a while, and we still reference that for CEO3. We'll talk about that in the conducted emissions session. And 461A came out in 1968, B in 1980, and then 461C, which is the one that we knew and loved for many years, came out in 1986. Then there was a significant shift when we went to D. Excuse me. When we went to D for both documents in 1993, there are significant updates to the requirements and test methods, and I think the most noticeable shift was in the nomenclature when the one prefix was added. So we went from CE01 to CE101, CS01 to CS101, RE10 RE02 to RE102, and so on. Now, in a lot of cases, that didn't really mark a very significant change in some of the test methods. The few of them it did, but like CE01 and CE101 are almost the same test methods. Same with CS01 and CS101. But that nomenclature shift seemed to throw people, and I think that's why we resisted going to more recent versions of this document for many years. But there it is. It went to a more general test as you fly philosophy, and that's where it introduced the application guide that provides a rationale and discussion of each requirement. And that's a very significant and very useful addition, where they actually started to explain to you what the test is for, what are you doing with it, and then tailoring guidelines that if your platform looks more like this, then it makes more sense to do this. So all good stuff to just help you do your job better. Then 461E was kind of another seismic shift when in 1999 that incorporated the test methods. So then Mil Standard 462 was canceled as a standalone document. So Notice 4 of Mil Standard 462D just canceled it as a document. You can still access them, and I'll show you the website where you can get them on another upcoming chart. But it was no longer maintained as a standalone document. So now everything was included in 461, and I think that's a change for the better, because now it's all in one document. There it is. Here's the test. Here's at least the default recommended limit, and then here's how you do it. So F was not as much of a seismic shift. That came out in 2007. And it just, minor evolutionary updates. Similar with G, and I certainly remember when G came out, because that's since I took this chief PMC engineer job. But again, that was minor evolutionary updates, not really a seismic shift. And this is where we are now. And then H is in progress, and I haven't heard any updates for a little while, but I'm sure that they're still working on that. I don't really know when they expect to have that out, but whatever. I'll be paying attention to any updates when I get them. So for system level testing, we had used these documents. I'm not going to read them, and you can see them right there. But they have since been superseded by Mil Standard 464, and first version came out in 97, and we've gone through a number of updates, and so we are presently at D, which came out in 2020. So if you look closely here, you don't have to. I'm going to point it out to you. 464B came out in October of 2010. 464B, Notice 1, came out just about 2 months later, and then the day after that, they released 464C. I don't actually remember what what the issues were, but clearly there were some things in B that were not desirable. So don't bother using that one. In fact, use D. You should use the latest version of any of these documents, which is a point I'm going to emphasize here coming up. But if you are ever referencing B, please stop. A note about International Space Station documents. Here's this list of documentation that we've used on space station projects. The core of them are the ones highlighted in the middle there, 302, 37, and 38. Those are basically, more than basically, they are tailored versions of Mil Standard 461C and 462, and they use the common nomenclature. And so they read very much like those documents. So if you're already familiar with 461 and 462, you'll be comfortable with that nomenclature, CE01, CS01, and so forth. And the website at the bottom there is where you can access those. I haven't tried to log in for some time. So you're going to have to request an account. I believe that that is a secure server, so you will have to request an account, and I think it'll take some time to get approved, and you're going to have to provide some justification. you're supporting space station projects or what have you. As I recall, it took a non-trivial amount of time before I actually was able to access that site. And since I haven't accessed it in a while, my account may have expired. So just be aware of that. But that is the site, at least the information that I have. So the mill standard documents are available at this everyspec.com site. That's just a public site. So you can go grab pretty much every version of any of these mill standard documents. And that's where I got them from. I've also put them in these folders on our working group teams document page. So including the ISS documents, I'd still recommend that if you're working on any, current ISS programs, you go to the actual site and get the real documents. And it's just kind of the best practice. But if there's something you want to look up quickly, you can at least pull the versions that I have up here in these folders. But again, just make sure that you're using the latest version of any of these documents. So a word about tailoring. Right up front in the mill standard, it says, and I'll read just the blue sentence here. When analyses reveal that the requirements in this standard are not appropriate for that procurement, the requirements may be tailored and incorporated into the request for proposal, specification, contract, order, and so forth prior to the start of the test program. So tailoring is welcome and encouraged. But I will place the caveat on there. It should be pretty well understood, but I'll hammer it home anyway. That needs to be based on sound engineering judgment and analysis, right? That you say this limit is way too stringent for what we're doing, and our analysis and our assessment show that if we reduce the limit to such and such, it still meets our needs, and it'll be much easier to meet, and we're gonna have a much lower chance of a lot of waivers and such, that sort of thing, as opposed to I don't feel like meeting that limit, it's too hard. And I've seen that. That shouldn't be a big surprise, but it's not I don't feel like it. It's we have this sound engineering basis for saying we're going to tailor the limit or the test method to better meet our needs. And I'll talk about, I have a few examples I'm going to show near the end of the presentation. So most of these documents, GEVs and mill standards, the shuttle document and the AIAA document, are not requirements documents. They provide a menu of options, not the meal. If you tell me that you are testing per GEVs or to mill standard 461, any version, if you just tell me that, and I've seen that like in some requirements documents where the entire EMC section, I've seen just like a single sentence, we're going to test per GEVs or mill standard 461. That's basically like me coming to your table as your server and you hand me the entire menu back and say, I'll have this. And maybe that is what you want. And I'll pull up a seat and watch you eat all that stuff and watch you turn green. But that's another story. Most likely that's not what you mean, right? So you need to actually specify what you want. And well, I said you need to, but what I mean to say is you get to choose the options. I mean, when you go out to dinner, it's not I have to eat all this stuff on the menu. It's I get to choose between pizza or pasta. What do I feel like tonight? Where in the case of your test program, you get to choose the options that make the most sense and define them in your project requirements document. So you're kind of empowered here, right? It's not being forced on you. You get to be an engineer and choose the options that work best for your program. And so think of it as get to instead of have to. You don't have to eat all that stuff and then become Mr. Creosote in Monty Python's Meaning of Life. Don't do that. I just watched that with my son a few weeks ago, so it's fresh on my mind. Anyway, the exception here is that the ISS documents are indeed requirements documents. They are pretty cut and dry. They have, I believe, it's been a little while since I've looked at them, but they do have some options as far as like what power bus you're on or which module you're in. But once that's clear, okay, you're going to be in this module, these are your requirements. So there's not really any room for tailoring there in ISS, or you have to negotiate that with ISS. But that's a bit more cut and dry, right? And so on the one hand, that's kind of constricting, but on the other hand, there's not a whole lot of additional work you have to do. You just know, all right, here are those ISS documents, and this is what we're doing. So, but just be aware of of your program requirements. If it's ISS, it's cut and dry. But if it's anything else, you get to make some engineering decisions using GEVS or MIL Standard 461 as guidance. So as a provider of electronic hardware for a spaceflight mission, you are responsible for knowing all of your requirements, EMI included, and how they will be tested. So a mechanical analogy, I'm being intentionally absurd here to make a point, but would you show up for a vibe test with only duct tape to mount your box to the table, then ask for a waiver when your box flies across the room and then ends up in pieces? And that's clearly rhetorical. But we get the equivalent, at least we used to. We don't anymore because I think, I think our message is getting across. Don't do that. But we used to get this kind of stuff with EMI all the time. People would show up for EMI tests clearly not prepared, and can't do that. You just can't do that anymore. You never could. And so, so anyway, I sum this up with great power comes great responsibility, from Uncle Ben Parker from Spider-Man, right? If you're responsible for building, electronic hardware for flight, you are responsible for making sure that you know your requirements and you're testing them properly. Okay, you still with me? I haven't heard anything. So is everyone still out there? Is anyone still out there?
Yep.
Yeah,
Yes.
we're here.
Still here.
Oh, yeah. The thumbs
Okay.
are flying.
All right, good. All right. So moving right along. Engineering concerns for EMI testing. Now we're gonna plunge a little further into it here. So here again, rather than just plunge into test methods, that's what we'll get into in the upcoming sessions. I just want to get across what are we actually doing? What are our engineering concerns? Because I think if when you understand the engineering concerns, then you understand a bit better why the tests look the way they do and what we're after with them. Okay, so one of the big categories is establishing compatibility with the power subsystem. Then there's compatibility with the radio frequency or RF communications subsystem. And then there's compatibility between subsystems, which is generally in the form of crosstalk, really specifically cable to cable crosstalk. So we'll talk about each of these in turn. So with compatibility with the power subsystem, I'm representing the power subsystem just as a battery here, simplistically. But you have your power source, battery or whatever it looks like, and then you'll have some distribution wiring or whatever conductors you have to get to your common distribution point. Okay. So whether it's traces on a PC board or wiring to a power bus, whatever that looks like, there's some conductive connection between your power source and the distribution point. So then you're going to hang a load off of that distribution point, right? I mean, the loads are what you're actually operating here, right? Power subsystem is great, but ultimately you're providing power to some load, and the load's going to draw some current. So on a DC bus, which is mostly what we deal with, but whether it's DC or AC, you'll have your nominal current that it's drawing to operate. So, if you're on a standard 30 volt DC bus, let's say your current draw is an amp, but then you're going to have some AC ripple current riding on top of that. That's what is going to form your conducted emissions. So then you're going to hang a whole bunch of other loads off of this distribution point, And all loads, really, it's all loads will see the total noise potential at the distribution point. So whatever noise currents all of those loads are drawing are going to produce a noise potential at the distribution point that everyone will see. And that is the basis of conducted susceptibility. You want to establish that you can withstand the worst case voltage ripple that's going to be at the distribution point that everyone will see. So conducted emissions limits are generally defined for individual loads. They pretty much are always defined for individual loads. I mean, for a unit level test, all you can measure is what is that unit by itself drawing. And it's in terms of voltage or current, as I'll go into in the next session on conducted emissions. I prefer the current measurements, but details forthcoming there. But the main point here is that the CE limits are defined for individual loads because you're only testing one load at a time. But your CS limits are defined for worst case composite voltage ripple at the distribution point. So I don't want to say it's apples and oranges, but it's not quite apples to apples. So in the next session, I'll talk about how we correlate those limits in a meaningful way. But you just have to be aware that your conducted emissions limits are for you only, but the CS limits are to provide an upper bound on what we expect everyone to see, or what kind of ripple everyone will produce at the distribution point. So for the RF communication subsystem, the entire raison d'etre of the radiated emissions electric field test, so RE102, is to protect antenna-connected radio receivers. That is its purpose, as stated in the MIL standard. And I'll quote chapter and verse on the next slide. Then the entire raison d'etre of RS-103, radiated susceptibility to electric fields, is to protect equipment from antenna-connected radio transmitters. This is right out of the MIL standard. This is EMC literacy right here. This is wrong with a capital R 3 times over. Okay, with a W in front of it. But, whenever you compare radiated emissions and radiated susceptibility, the electric field limits, you're putting square pegs in round holes, and it doesn't work very well. It doesn't work at all. You're not supposed to do this. The way you have to think about this is that a properly defined radiated emissions limit is defined to protect any radio receivers that are operating in that frequency band of interest. What the radiated susceptibility limit is in that frequency range is completely beside the point. So when you use that whatever the RS limit is as justification for a waiver for an RE102 exceedance, you're in this zone right here. And don't do that. Don't accept any waiver request that uses that as a justification. Okay. So another tidbit I'd like to throw in here is, here in the NASA environment, we are pretty much always, or most of what we do is build onesie twosie things, right? So that's not what the MIL standard was written for. It's a military standard, MIL standard 461. So it was written for primarily, really, it was written for military programs, and NASA just adopted it. And for the most part, it works pretty well. But here's one place where you have to keep that distinction in mind. If I pretend that I'm a contractor building transponders for military platforms, I'm not looking to build one transponder for one mission. I'm looking to sell this transponder to any program that wants it, ideally dozens or hundreds of them. So if I'm looking to get military contracts with it, then basically the approach is that in the MIL standard, it's if you want to fly on any military vehicle, then you're going to have to meet this stringent limit across this very wide frequency range. And that's how you have to think about that and why those limits are defined the way they are. For NASA missions, we have very very specific radio receivers and transmitters, and certainly at the beginning of the program we might not know the specific frequency of, say, our S-band receiver, but we at least know the range of frequencies. We know we're going to be in S-band, so we can be at least focused on that frequency range of concern. I've worked several programs where the only receiver they have is S-band. That's the only one we have to worry about. And that's a much different problem than having to build something that can be compatible from 10 kilohertz up to 18 gigahertz. So it's just something to keep in mind when we're taking these MIL standards that were written for a specific purpose, and NASA is repurposing them differently, right? We're taking them and we're using them for a little bit of a different purpose. The general idea of establishing, compatibility with your radio equipment is the same, but the specific way we're doing it looks much different, and we have to think about it differently. Okay, I hope that helps. But this point comes up over and over again, and this is one thing I really hope does not continue once I leave, right? Because this still comes up, and this is EMI illiteracy, right out of the gate. And so if you see somebody using this as justification, it is not correct, and call them out on it. So here again, right out of the MIL standard, chapter and verse, there is no implied relationship between RE102 and RS103. Attempts have been made quite frequently in the past to compare electric field radiated emission and susceptibility type requirements as a justification for deviations and waivers. I am not making this up. This is right out of the MIL standard. Okay. And another statement from that same section: it may be desirable to tailor the frequency coverage of the limit to include only frequency bands where antenna-connected receivers are present. We generally take that to be above 200 megahertz for Goddard platforms. And I'll have more to say about that here in just a minute. And then the last point on this chart is the cables are part of the EUT. There's similar wording under RS103, but it says very clearly here, the requirements are, this is still for RE102, by the way. This is all out of the application guide. So sort of a public service announcement for the utility of the application guide to tell you why we do things. The requirements are applicable from 10 kilohertz to 18 gigahertz for electric field emissions from the UT and associated cables, emphasis mine. So the cables are part of the EUT. So here's the general setup, EMI setup diagram per GEVs. It's tailored from MIL standard 461G. We'll talk about this here in a little bit, where we replace the LISNs with feed-through capacitors, but otherwise it's pretty much the same setup. But it's very specific about defining the layout for cables. So the interconnecting cables are part of the equipment under test. So common mode energy in the EUT can and will couple to cables, which can and will radiate, particularly in the frequency range where the cable lengths are significant fractions of a wavelength. They will be your most efficient radiating element, right? Generally in like the tens of megahertz to a few hundred megahertz. That's when a couple meters of cable is gonna be right in its range where it will be your most efficient radiator, much more so than seams on your box and things like that. The connector seams and things like that are a couple centimeters long, they're going to be more likely to sing up in the gigahertz range, just because that's where the wavelengths are going to be shorter. But these cables, when you energize them with common mode energy in that frequency range, they will sing like songbirds, and that's what we see when we do these radiated emissions tests and susceptibility. So the common mode energy in the EUT can and will couple to these cables, which can and will radiate, and then incident radiated energy can couple to cables, which then will carry those common mode currents into the EUT and possibly cause disruptions to your circuitry. So a properly designed box level test with flight representative cables, as they are required to be, and representative loads exercises the cables as much as the electronics box. So I submit that there is no such thing as a box only level EMI test. And shortchanging the box, or what I would call a subsystem level test, only invites additional risk at higher levels of integration, thereby totally defeating the purpose of these lower level tests. So don't shortchange the cables and don't shortchange your box level test. This is your best opportunity to identify potential problems and fix them, because you don't want to be doing that once you integrate onto the platform. There again, project managers don't and systems engineers don't like that very much when you've got a problem at the integrated platform level that you should have found at the lower level, or worse, that you knew about and didn't fix. So when an EUT meets RE and RS requirements on a military platform, there's generally a low risk of crosstalk, because that default RE102 limit corresponds to common mode current levels on culprit cables that are too low to pose a significant risk of crosstalk. So it's pretty much saying the same thing. RE limits that protect radio reception. When you think about a radio receiver, is by design the most sensitive victim on your platform, by and large, right? It's specifically designed to be sensitive to very low level RF signals. So it's going to be more sensitive than anything else, right? So if you meet those limits to protect radio reception, then you have a very low risk of crosstalk. But outside of those radio bands, the default limit may be significantly relaxed. And this is precisely the reason that RE102 exceedances have historically been the largest sources of waivers on many Goddard platforms, and why I said on Monday why Rodney Dangerfield has been our patron saint. I mean, you have these very stringent limits in the receiver notches, but outside the receiver notch, the limit is tens of dB higher, because you don't need that kind of control outside of a band of a radio receiver. So when people don't understand that distinction, I've seen where it's easy to lapse into the thinking, well, none of these RE limits matter. And when we grant waivers for exceedances that are tens of dB above the limit outside of a receiver band, because that limit is meaningless. But inside the receiver band, it's a non-negotiable. You have to meet that. So most Goddard platforms do not use antenna connected receivers below 200 megahertz. So following this guideline, per GEVs for Goddard platforms, we apply RE102 only above 200 megahertz. And more coming up on that very shortly, maybe the next slide. So the crosstalk is the dominant concern below 200 megahertz. And I love this quote from the late great Henry Ott. Conducted emissions limits are really radiated emissions limits in disguise. That was the point I made earlier, that they're one and the same. Whenever I hear anybody say, "Oh, it's not a radiated problem, it's a conducted problem," well, it's kind of both. Just which one is dominating. So, okay, here we go. So this is from the RE102 section of MIL Standard 461. If you're not familiar with this document, I highly recommend you do so. I will be the first to say that, I mean, it's not like reading. I was going to say not like reading a bedtime story. Maybe it kind of is, because it might well put you to sleep, but bear with me. It's not like reading a thrilling adventure story. So it's most useful when you pick it up and read a little bit of it at a time. Like you read through some of the preliminary, the kind of stuff that we're talking about now, or you're curious about a particular test method, RE102. Like you go to it and just read a little bit more about that method to learn a little bit more about what it's saying. But anybody involved in EMI testing and in any capacity really needs to be familiar with this document. So many of you are already familiar with this diagram. And we'll talk about this more when in our RE102 session. But one thing I'm going to highlight now is that when you say you're doing RE102, that means that your test antenna is placed 1 meter from the test setup boundary. That's a thou shalt. That's non-negotiable. And I'll have more about this in the RE102 session, but it has to do with the fact that you are very much making a near field measurement. Yeah, in the far field, you can be a little bit more forgiving with antenna placement. If you're truly in the far field, it means that your wavefront has constant power density, and you can place the antenna more or less anywhere along that wavefront and get the same answer. But when you're in the near field, uh, that's very much not true. And so these antennas are calibrated at very specific distances. So 1 meter for mil standard testing, and then 3 meters and 10 meters for commercial testing. For that reason, to account for the fact that you're not dealing with a uniform wavefront coming off of the EUT. I mean, just look at this visually. I mean, it's probably not entirely to scale, but it's sufficient to get the point across that if you got an antenna of this size, a significant chunk of a meter, it's probably 60 or 70 centimeters, 1 meter from your box, even if your box is behaving as an ideal point source, which it most certainly is not, but even if you assume this is an ideal point source, you're still dealing with a spherical wavefront out here, assuming everything is still well behaved, which it probably isn't in the near field. The whole point is these antennas are calibrated at these very specific distances to account for all that. And if you muck with that, then you're going to get less reliable results. So that's just one of these things for understanding these test methods and why things are specified a certain way. You get some flexibility in some things, but this 1 meter distance is not one of them. And the next slide, I'll emphasize the point I'm making with that. Then, so the other point here is we have an antenna configuration break at 200 megahertz. And so that makes it a convenient breakpoint for we test radiated emissions above 200 megahertz, and we test cable-to-cable crosstalk below 200 megahertz, because that's what our concern really is. What do you know? That's exactly what my next chart says. So dominant concern below 200 megahertz is cable-to-cable crosstalk, which RE102 and RS103 do not effectively address. The entire point I was making on the previous chart, RE102 specifies a 1 meter measurement distance. I don't believe I've ever dealt with a cable crosstalk problem where cables were a meter apart. That's just not a concern. We're almost always, if we have a crosstalk concern, we're talking about cables that are very closely spaced, like a centimeter or two apart. And so any attempts to correlate the measured field at 1 meter to an expected field at a few centimeters is non-trivial and carries very large uncertainty, to put it mildly. If any of you saw my dipoles presentations in the fundamentals sessions, I talk about this a bit, but if you use your far field your far field relationship where the field drops off as 1 over R, and you say, well, okay, I'm 1 centimeter in, so my field must be 100 times higher than what I measured at 1 meter. Don't do that. Don't even use the 1 over R cubed, okay? Because those relationships for a Hertzian dipole are still assuming a point source. So if you're trying to look at 1 or 2 centimeters away from a long cable, you're not looking at a point source. So any of those equations, even for near field predictions, are really fraught with peril. I mean, you're really kidding yourself that you think that that's going to give you an accurate answer that you can actually use for anything. So don't do that. So this is all much more efficiently addressed with direct measurements of common mode currents on cables. So common mode conducted emissions, and then susceptibility using the CS114 test method. And fear not, I've got full sessions on each of those topics. So common mode and differential mode I'm planning to cover together next week, and then we'll talk about CS114 in another session in several weeks. But this gives you a much more direct way of assessing the risk of crosstalk than you will ever get with RE102 or RS103. So some updates in mil standard 461G, as in from F. When they went from F to G, some updates that were put into Rev G. One had to do with the use of fast Fourier transform, or FFT, receivers for emissions testing. So FFT receivers have been demonstrated to perform emissions testing significantly more quickly and efficiently than traditional frequency swept techniques. We have a couple of them at Goddard. That we were able to get projects to invest in them when we made the case that without them, their radiated emissions testing program for a single project was gonna take some ridiculous amount of time, probably weeks. And if they invested in one of these machines, we could do it in an afternoon. And it went from, my God, we can't afford such a thing, to how fast can we get one? So just another completely non-technical thing I'll pass along here is that when you're able to put things in those terms for your management, you can actually get them to invest in some really good test equipment to help you do your job better, and it helps them with cost and schedule, which is what they care about. But anyway, I can't say enough about these machines. They've really transformed the way we do emissions tests here at Goddard. And transformed. I didn't even do that on purpose. So hey, a pun a minute. I'm here all week. Tip your waitress. Anyway, is anybody still there?
Yep, still here.
Oh yeah.
Okay.
Yeah, still here.
You were all muted when you were groaning at my dad jokes. That's okay. I'm preparing for retirement. I'm entitled to a dad joke or several here. But anyway, so but the second point here is that with any new toy, you need to be careful about how you're using it, right? That if you don't actually know how to use it properly, you can get bogus results. So MIL Standard 461G provides, I say requirements, I think it's really more guidelines, but guidelines for performing these FFT measurements correctly and consistently with existing measurement techniques. Right, you want to get, if you're using the FFT machine, you want to get results that are still consistent with the traditional way we have done them, with the frequency swept techniques of the more traditional machines. Okay, but that's one of the things that's in the updated version of the document is that it gives you instructions for how to do that, or at least, certainly guidelines. Another big one I like to cite is calibration of measurement equipment. For your primary measurement devices, oscilloscopes, the things that you're actually using to give you a number for the thing that you're measuring. So spectrum analyzers, receivers, oscilloscopes, multimeters, that sort of thing. Those still need to be calibrated in accordance with an approved calibration program traceable to NIST. Okay, that doesn't change. But passive devices, such as measurement antennas, current probes, LISNs, and so on, require no further formal calibration unless the device is repaired. Those types of things don't generally change their calibration unless you drop them and break them or damage them. Right. So if you have some device repaired because you dropped it, then okay, it needs to be sent out for cal again. One other thing I'll point out, I'm not in the lab where I could show you this, but current probes you can calibrate yourself. You can get these calibration fixtures. I mean, ideally, right? Certainly for higher frequency current probes, you should use a proper calibration fixture built for that probe. But I have one. I think I have a couple of them actually. They're not terribly cheap, and I think they're actually more expensive than the current probes I calibrate with them. I think the one that I bought, it was like $8,000 or $10,000. But still, think of it as an investment. For $8,000 or $10,000, you have a fixture that you can use to calibrate your own current probes periodically. In the long run, I think it'll pay for itself probably in one test campaign. Maybe a few, but whatever. Having your own test, it's just something you put a controlled current in and you measure the voltage out. That's what the calibration factor for a current probe is. And you run it into a network analyzer that should be calibrated. and you do it yourself. But the point is here that the mill standard allows you, 461G allows you to do that, where previous versions didn't specifically say that. They said everything needs to be calibrated. So here again, it's something to help you do your job more efficiently. And then the measurement system integrity check is sufficient to determine the acceptability of passive devices. And I'll talk about that, the measurement system integrity check, near the end of the presentation. But that's when you put a known signal into your measurement setup and verify that you're getting out what you expect, and that's considered sufficient to establish that your devices are working properly. So these are just advantages to using the latest version of a document. This is one of my, call it a mantra or pet peeves, really. Whenever I hear, well, we're under contract for Mill Standard 461E or C or whatever version is called out, I will never understand to my dying day or my retirement day or whichever why people do that, because if you're deliberately avoiding even looking at Mill Standard 461G, you're missing stuff like this that is specifically there to help you do your job better. So they update these documents for a reason. So in any requirements document that I have any control over, any input in, I always, in like the reference documents list, I always put in a statement that the most current version of any of these documents should be used. If it's should, you get some weasel words, because if you say shall, then people get all up in arms. But just a very, very strong recommendation that that you use the most current version of any of the documents that you're referencing. They get updated for a reason, so you owe it to yourself to know what's in there.
Some say that if you leave the version off, that means the latest. Is that correct?
That's what I do. I generally don't put in the rev number, but yes, right. Don't put the rev number in, and just have a statement saying that the latest versions of all documents is what should be used. You may get into disputes with your systems engineers, but that's what I try to go with, and I stick with that wherever I can. All right, so getting into the test facility and procedure requirements from the mill standard. Those are defined in section 4.3, the mill standard. So definitely recommend you get familiar with that. I think somebody still has a hot mic. So if you can mute when you're not asking a question, please. So test facility procedure requirements defined in the mill standard, section 4.3 apply with modifications as discussed in GEVs. So I'm going to go through these one by one. And I have a couple of additional things that I'm not listing here, but that aren't specifically tailored in GEVs, but just I want to make a few points here. So first thing here is ambient electromagnetic level in 434. I'll just read this. During testing, the ambient electromagnetic level measured with the EUT de-energized and all auxiliary equipment turned on shall be at least 6 dB below the allowable specified limits when the tests are performed in a shielded enclosure. So the significance of this is that the noise floor or the RF background level, it's basically going to, whether it's background or whether it's noise floor, is going to contribute more or less the same way in this discussion. That if you think of just any signal and any noise or our background is going to add, right? It's just a matter of degree. So if the signal, well, let's take two correlated signals, right? If you have two signals at the same amplitude and they're correlated and synchronized sinusoids, then the amplitude is going to double, or in dB space, it means that it will be 6 dB higher. The amplitude in terms of voltage or current or electric field, it'll increase by 6 dB as compared to the amplitude of either signal by itself. Now, if your second signal is just noise, and noise is just a signal that you don't want, but if it's uncorrelated, then the signals will add in quadrature or RSS. So it means that the combined level that you will observe will be 3 dB higher. If your signal that you're trying to measure is right at the noise floor level, if in real life an objective measurement would tell you that it's right at the noise floor level, well, now you're superimposing that on a noise floor with the same magnitude. The total amplitude that you're going to measure is 3 dB higher. Okay, so you're going to get this indication that your signal is 3 dB higher than it really is because the noise floor is adding to the total thing that you're able to measure. Okay, everybody with me? This is important stuff. I want to make sure you understand it. For a future version of this, I might include some charts to illustrate the point. But so for any combination of signals, signal noise ratio, you can do that same math of the levels adding in RSS manner, or you can also say that the power levels add. And I actually have another session on test and measurement where I go through some of this stuff in more detail. But the 6 dB number is chosen such that if you do that math, where a signal that is 6 dB, if the signal that's right at the limit that you're trying to measure, and your noise floor or background is 6 dB lower than that, when you do that math, the RSS math, then the apparent signal that you will measure will be 1 dB higher, 1 dB above the limit. Okay, so you're still going to get an artificial indication that you're above the limit when in reality you're right at the limit. But 6 dB was just chosen as okay, if your noise floor or your measurement system level, your noise or background level is 6 dB below the limit, that's considered sufficient to at least be a minimal contribution to the level that you're measuring. And we're generally not terribly concerned about 1 dB problems with EMI, right? So that's basically why that 6 dB level was chosen. I mean, you could have said, I mean, in this other session, I go through the numbers where, like, if your signal noise ratio is 20 dB, if your signal is 20 dB above the noise floor, the noise is contributing about 0.1 dB. And if it's 30 dB above the noise floor, the noise contributes like 0.01 dB, right? So it's all a matter of degree. And so what is sufficient? You could insist that your noise floor be 30 dB below the limit, but then you're getting into overkill, and that just gets more difficult to achieve. So 6 dB, it's always that balancing act. Like what is good enough? What is good enough to facilitate a decent measurement that people can actually meet without jumping through hoops of fire. So I hope that helps. If you can get your noise floor 20 or 30 dB below the limit, so much the better, but that gets to overkill. So one of the main things to address the ambient level is don't run your cables, your test cables in your setup. Don't just run them through a hole in the wall. Okay? Because common mode currents are going to generate fields. They're going to generate magnetic and electric fields. And if you just run them through a hole in your chamber feed through, they're just going to bring those fields into the bring the common mode currents into the chamber with them and generate fields that are going to corrupt your ambient level. And it's going to make it harder to meet that 6 dB limit, and it's going to make it harder for your unit to pass an emissions test. So do this instead. Make sure you terminate your shields at the wall, and then run the cables over a ground strap. Nice wide copper strap is ideal, and it provides a path for those common mode currents. That it'll stop them at the wall ideally, and then it provides a path for those currents to get back to their sources in the EGSE. EGSE noise is a really common problem with EMI tests, and you want to minimize how much time you're chasing apparent problems that are due to your EGSE. So when we scream and yell about doing things this way, about having proper cables, I'm sorry, we never scream and yell. When we ask you gently and politely to do things this way, we have your best interests at heart because we want to make best use of test time. I think that's what everyone wants. But when you have when you're failing your emissions tests miserably, and you spend hours or days chasing them down to what end up being EGSE problems, that's not a good use of test time, especially if it's something that we know how to prevent or at least minimize that risk. Terminate the shields at the wall and run a nice copper strap back to your EGSE rack, and that will minimize how much of this crap gets into the chamber and corrupts your test environment. The preferred method is just provide a connector break at the wall, and then you terminate your shields to back shells, to metallic conductive back shells on both sides. An alternate method is a stuffing tube. You know, to remove the jacket, the insulative jacket from the outside of the cable to expose the shield, and then run some metal wool, steel or copper wool, between the cable and the feed through tube. Now, I've never seen anybody do this. I know people who have, but I think when you give people a choice between mucking with their test cables and stripping the insulation off the outside, or just building the cables properly with a connector break, most people choose this, especially since they're, these cables are basically going to get you through your entire environmental test program, including thermal vac. You're going to need a connector break anyway to get through the thermal vac chamber. So, just plan ahead, build the cables properly. And especially if you're doing this anyway for thermal vac, this really shouldn't require any additional work. Just plan it properly. Use one set of test cables for everything you're doing. So the mill standard specifies that the UT shall be installed on a ground plane that simulates the actual installation. If the actual installation is unknown or multiple installations are expected, then a metallic ground plane shall be used. So any EMI chamber will have a nice copper ground plane. It's unfortunate that I'm not able to be in the lab today to show you. I was able to show it on Monday. You can look at the video of that session if you like. But the ground plane shall have a surface resistance no greater than 0.1 milliohms per square. I'll talk about per square here in just a moment. And then the DC resistance between the metallic ground planes and the shielded enclosure shall be 2.5 milliohms or less. That's what's specified by a Class R bond, by the way, in NASA Standard 4003. And then the metallic ground plane shall be electrically bonded to the floor wall of the basic shielded room structure at least once every meter. And there again, in another session, I can show you how we do that in the lab when I'm actually able to be back in the lab when we do conducted emissions. And the metallic bond strap shall be solid and maintain a 5-to-1 ratio or less in length to width. That's also right out of the spec for a Class R bond in NASA Standard 4003. So just this ohms per square. What does that mean? Ohms per square what? Well, I think most of you know this, but just for reference, if you just take a square of stuff, some material, and just take a square of it, it's going to have just some inherent bulk resistivity. And so if we have some length, calling this dimension length, and then width, and then thickness, and for a square, the length and width are the same, right? So the resistance across this dimension here, as I'm showing it, the cross-sectional area is going to be this is going to be W times T if we're talking about the resistance in that direction. And so the resistance for that square of stuff is going to be rho L over A. So just the standard relationship between bulk resistivity and resistance. Okay. So we take that square of stuff, put another square of stuff next to it. So the total resistance that I'm going to call R2 for two of these squares in parallel is just going to be half of R square. Take two more of them, put them in series. Well, okay, so the resistance of four of these things making a larger square is just going to be 2 times R2, which gets you right back to R squared, or R square. So the resistance is independent of the size of the square. So that it's ohms per square, QED. So I'd gotten into a nice little debate with somebody when I had spec'd something out in terms of ohms per square, and they were arguing adamantly that I needed to include what, ohms per square what? Per square centimeter, per square meter? And I had to, I think I already had these charts prepared, and I said, no, it really is ohms per square. That is how you define resistance of a ground plane. So anyway, there you go. And then just to finish up this, we go back to this original discussion here where the R square is rho L over A. Well, our area, our cross-sectional area is just WT, and we've said that L and W are the same, so are equal, so they cancel. So the resistance is just rho over the thickness, right? Resistivity over the thickness. So if we take an example of just a 1 millimeter thickness of whatever our stuff is, and if our stuff is copper with its resistivity of 1.68 times 10 to the minus 8 ohm meters, weird units for resistivity, but there it is. That means that a square of copper that's 1 millimeter thick will have a resistance of a little bit less than 0.02 milliohms per square. And if it's aluminum, it's about half again, a little more than half again higher resistivity. But there again, the resistance is a little less than 0.03 milliohms per square. So it's really not terribly difficult to meet 0.1 milliohms per square. If you're using either copper or aluminum, and you're a millimeter thick or more, this is very easy to meet. So if anybody is griping about if they think that 0.1 milliohms per square or even 1 milliohm per square is really stringent, it's not. It's really not very hard to meet this as long as you're using just a good conductive material. Okay, so moving right along here. Power source impedance. Everybody good so far? Everyone still with me?
Yep.
Okay, good. So let me jump ahead here. I'll come back to this, but the comment on Monday that it would probably be helpful if I put this chart first, in this section. But just going back to the chart I showed earlier, with the power distribution architecture, you have a power source, common source impedance, distribution point, and so forth. This discussion about Lisons that I'm starting here is addressing this common source impedance. Okay, so this provides context for what we're talking about. So I didn't have a chance to address this and modify the charts accordingly, but I want to remember to do that. Anyway, this is the context of this conversation right now, is this common source impedance. So going back here, so you're talking about some conductive connection from your power source to the distribution point, and thinking of it as just conductors, that's the most straightforward thing, right? So it's going to have some conductor resistance, but it's also going to have some inductance. You have no choice, right? You go up in frequency, the inductance of that configuration is going to come into play. And then at higher frequencies still, you're going to see the characteristic impedance of the transmission line that you're forming between those two conductors. And again, that's physics. It will behave as a transmission line at high enough frequencies, and so it just will. You don't have a choice in the matter. So this is more in line with how it physically looks, like the resistance of both conductive paths. It'll be shared between the two paths, but we can simplify the model by just combining all of those impedances on the positive leg here, just mathematically and conceptually. And the impedance is just the parallel combination of R plus j omega L in parallel with Z naught, with the characteristic impedance, the way we've drawn it here. So we just work through the algebra and divide top and bottom by Z naught. And then we note that R is generally going to be much less than Z naught. Okay, Z naught is generally in the tens or maybe hundreds of ohms, and R is in like the milliohms to tens of milliohms. So by and large, we can basically just set that term equal to zero. We can just remove that, simplify the expression as we see here, and then when we graph it, well, what do we do with this? I find it helpful to break things down into frequency ranges. So at low frequencies, where you can basically set omega equal to zero, you're left with R, right? These terms go away. So it's just the wire resistance is what dominates at low frequencies. So you have this plateau here that's just R. The mid-range of frequencies, you're left basically with J omega L. So it's the inductive reactance is what's going to dominate in this linear part of the curve here, or this sloped part of the curve. And then at high frequencies, where you basically set omega equal to infinity, that's where these terms dominate, and then everything cancels except for Z naught, right? So at high frequencies, it's where Z naught dominates. So this is a very typical impedance curve for harness or just any conductive connection. Low frequency resistance, inductance, and then characteristic impedance. So this is what goes into these things we call lisons. So there are two answers to that question of what is a lison. You can't make this too simple. But the first definition of a lison is a line impedance simulation network, which is basically has the topology of what we just looked at. So I find it conceptually straightforward to think of this one first. So it has your resistance and inductance, and then your shunt high frequency resistance. So it simulates the line-to-line impedance of your power source and wiring to the distribution point. Now it's generally dominated by that wiring to the distribution point, because if your power source is a battery, it should have as close to zero source impedance as you can get. You're really going to be dominated by the connection from the battery or power source to that distribution point. And this is generally a self-contained unit. When you're using a lison that is a simulation network, you generally are getting a box with all of this stuff in it. And again, I'm not in the lab where I can show you some examples, but you can watch this section of the video from Monday to see some of those that I showed. So the other definition of a lison, it's pretty cool that we an acronym means two different things, but here we are. It's also a line impedance stabilization network. This is really, I think, the more traditional or more common usage. But it provides a stable line to chassis impedance from the power source and the wiring to the distribution point. And the high frequency 50 ohm shunt impedance is provided by the input of the measurement receiver. So this type of lison here has a measurement port here that goes to the 50 ohm input of a measurement receiver or whatever your measurement device is. You could hook it up to a scope too, but it's generally hooked up to a measurement receiver or spectrum analyzer. And I say the Thevenin equivalent source impedance is left as an exercise for the interested viewer. But basically, when you do I actually wanted to put together, just a refresher on Thevenin equivalent analysis, because we do that all the time. And I'll be doing that in upcoming sessions. But if you short out your power source, and at higher frequencies, these capacitances are basically short circuits. But really, this is the only one that matters. When you short this out, you're not seeing any of this stuff anyway. But to determine your source impedance, you short out the power source, and if at high enough frequencies this is basically a short, then you've basically got your 50 microhenries or whatever this inductance is in parallel with 50 ohms. So you have something that essentially looks like this, but without this resistance here. It's just an inductor in parallel with 50 ohms. So it gives you you can hook up a 50 ohm coaxial cable to go into your 50 ohm input of your measurement device. So you're in a nice 50 ohm system there. And that 50 ohms also is what provides you that 50 ohm shunt impedance. You don't need to include that in the box. Now, these come in pairs, generally speaking. So if you're using these things, you would need a lison on each of the positive and negative power leads. as opposed to the stabilization network where it's giving you the impedance on both of the positive and negative power leads all in one unit. So we go back to our power distribution diagram. The LISN represents the common source impedance at the distribution point. It is not intended to represent the wiring impedance from the distribution point to individual loads. This is an important distinction, and I think this gets confused. I see this get confused, where people define a LISN thinking that it needs to represent this entire impedance, and that's not correct, and it's a misunderstanding of what the LISN is for. So if you think of just the power distribution in your house or in any building, and also on any large military platform like an aircraft carrier or something, basically follows. I'm using my imagination here because I've never really supported any program like that, but I imagine that they have standard 60 hertz, 120 volt power distribution on those military platforms so that sailors can plug in their radios or laptops or whatever into standard outlets, right? So in any large platform, large building or whatever, you'll have individual circuits coming off of your distribution panel going to a section of the building. Like whatever room you're sitting in, all those outlets are probably daisy chained together and might be daisy chained with a whole group of rooms in that section of the building. I think in my house, like all of the outlets in the upstairs might be ganged together. I don't remember. I did the rewiring in my basement when I did that about 20 years ago. But anyway, your mileage may vary, but clearly in any building, a whole bunch of outlets are going to be daisy chained together. If you've ever done this wiring, or even opened up a panel and seen it, the wires come from the panel. One pair of wires or three wires comes from the service panel to the first outlet in the chain. And then the rest are just daisy chained from there, generally speaking. So the wiring back to the circuit breaker panel can be quite long. It could be tens of meters, or if it's a large building or large platform, it could be hundreds of meters. You don't really know, right? You have no idea unless you've actually traced out the wiring in your office building. You don't know. This could be hundreds of meters away. So that common source impedance can be quite high, and you don't really know what it is, right? But on a spacecraft, we generally are doing things quite a bit differently. I mean, conceptually, it's the same basic diagram, but we generally are running dedicated power wires from each load back to the distribution point, and we want this distribution point to be as close to the battery or whatever, or the power source as possible. And in some cases, some of the recent in-house programs I've worked, that distribution point, just in talking to our power group at Goddard, that distribution point in some cases is on a printed circuit board inside the power distribution unit or whatever equivalent that it's called. It's inside on a circuit card with thousands of microfarads right at the distribution point. So it's not necessarily going right back to the battery, but it's going back to the next best thing, lots of capacitance at the distribution point. So that common source impedance is typically much lower. So in this type of topology, we don't generally have significant power quality problems on spacecraft. But because the common source impedance is so low, so you can generally tolerate a fair amount of noise on any individual load that nobody else is really going to see, or it's way below any of the levels that anybody's going to care about. So know thy platform. That's one of my mantras, right? So if you're using a LISN with a ridiculous amount of inductance on a platform like this, you're not knowing thy platform. You're not really applying a meaningful technique to your tests, which is well, we'll go through some examples here, but I'll hammer that point home in just a second. This is at least one ISS LISN. I think there are a couple of different varieties depending on which power bus you're on. But this is right out of the SSP 30238 document. But this is a line impedance simulation network the low frequency resistance, the conductor resistance is outside of this parallel combination here. So the topology is a little bit different, but it doesn't really affect the overall impedance that much. You know, if they had put this inside with the inductor, like the more typical topology that I drew, I think you'd still essentially get the same curve. So, but the point is that this is a simulation network topology, not a stabilization network. So Lisons are generally defined by the inductance value. So you might be inclined to call this, I think I've probably called it a 10 microhenry Lison. But note, there are two of them. There are two inductors here. So the total inductance really is 20 microhenries. So it's more accurate to call this a 20 microhenry Lison. But, you know, but just pay attention, right? If you've got two inductors in there, then the total inductance is twice the value that you might be quoting, you know. Um, Mill Standard 461 specifies the default 50 microhenry Lison that I was showing on the earlier slide. And that is a line impedance stabilization network. So this 50 microhenry inductor, that inductance that's going to simulate the line inductance in the lower part of the curve here. And then the 50 ohm termination of your measurement device is going to give you it's going to simulate the characteristic impedance of the line. Now, the actual characteristic impedance of a line in this configuration is probably a few hundred ohms, but they've just standardized this to 50 ohms, you know, so basically, you know, to use a 50 ohm measurement system. I don't know the full ins and outs of that decision, but that's basically what I understand to be the case. But if, you know, I'll go through this architecture here, make the point again. But this is intended to simulate the worst case power distribution wiring on large military platforms. So like aircraft carriers or aircraft, or, you know, any large item, large platform. The power on those kind of platforms, the power it tends to be distributed as a single wire 5 centimeters above chassis. And the structure is used as the intentional current return path, which we generally don't do on spacecraft. So this configuration will have an inductance in my inductance and magnetic session in the fundamentals sessions. I go into some details about that, about how you can calculate the inductance of these configurations, but that will have an inductance of about a microhenry per meter and running as much as 50 meters to a common distribution point. So think of like in a building or on a large platform, you're running that one set of wires out to the distribution point where your loads are going to be ganged together. So that's where you get the 50 microhenries. And that configuration, a wire 5 centimeters above chassis, is going to have a characteristic impedance of about 300 ohms. So the 50 ohms is an approximation but it allows you to use readily available test equipment and use that 50 ohm system, because at RF, being able to use a 50 ohm system and impedance mismatching, you know, it helps you get controllable and repeatable measurements. Really, so the basic point is this is not realistic for Goddard platforms. This is not how we distribute power on our spacecraft. So the Mill standard specifies this alternate 5 microhenry Lison. So it's largely the same topology, just with a 5 microhenry inductor instead of 50. This may be more realistic for smaller platforms, but it's still probably overkill for most of what we do. Right. And on Monday in the lab, I showed some examples of these Lisons, and I had a 5 microhenry Lison opened up. This is where we have to. It's unfortunate I can't show you this right now, but you know, if you look at this section of the video from Monday, you'll see. But the 5 microhenry inductor inside that Lison is quite big. It's on a piece of I believe like 3-inch diameter PVC pipe, and it's wound for about 4 inches along it. And the basic point is that's what it takes to get 5 microhenries. That's a lot of inductance, and you don't get that by accident. You don't get 5 microhenries of stray or parasitic inductance. you have to mean it. You have to get 5 microhenries on purpose. And 50 microhenries, the point is ever more present. In the 50 microhenry Lizen, I think it's like a 4-inch piece of pipe, and it's wound for about a foot. This is a lot of inductance. And when you're routing power the way we do on spacecraft with a dedicated wire twisted with the send wire or groups of wires, you're not getting a microhenry per meter. You're getting maybe 100 nanohenries per meter, thereabouts. And we're not running for 50 meters. We're running for maybe 10. So 1, maybe 2 microhenries is a bit more realistic. 5 microhenries is even that's overkill, and 50 is just way over the top. There is no reason we should ever be using a 50 microhenry Lizen on any of our Goddard spacecraft, unless there's something really unusual about them. So for Goddard platforms, the power source impedance is more accurately represented by a capacitor network. You have this pair of 10 microfarad feed-through capacitors installed between each power conductor and the ground plane. This is an integral part of the standard setup specified by the old mill standard 462. So this is one of the reasons why we do still reference those older versions of the mill standard, because this gives us something that's much more useful for what we do. They're part of the standard suite of equipment available in any EMI lab. Any EMI lab that's been around for any length of time will have these capacitors. Again, I can't show them to you today, but they're about 3 or 4 inches cube, and every EMI lab will have them. So you're not talking about buying any new equipment here. And it provides a standard source impedance down to about 20 kilohertz. It's about an ohm at 16 kilohertz, I believe. So, but approximately 20 kilohertz, it's about an ohm, and then it just gets low. 1 over j omega c. The impedance is lower as you go up. Then the 10,000 mic line-to-line capacitor, it extends that standardized source impedance down to 30 hertz. That's the low end of our test methods. The conducted tests go down to 30 hertz, and it's intended to simulate a battery impedance, right? And this capacitor network replaces the Lizens in mill standard 461 based setups as we specify them in GEVs for Goddard platforms. And one other point I'll make here: the 10,000 mic capacitor, those are readily available from DigiKey or any equivalent outlet. I've bought 3 or 4 of them for maybe $100 a piece, and you can get them in a couple 3 days. So the point here is that your lab almost certainly already has these 10 microfarad feed throughs. And if they don't have a big cap like this, there's nothing real magical about this specific value. If they have a 5,000 mic readily available that can handle the voltage and the power, or great. But if you don't have one of these, you can get one very quickly for $100. Where a custom Lizen, I have specified and purchased a custom Lizen, and as I recall, it was about $10,000. So there again, if we go beyond the technical and just look at the cost implications, this is much more cost effective, and it's a better engineering solution for this type of platform. So okay, a few words about cables. Electrical cable assemblies shall simulate actual installation and usage. The real point here, you can read the remaining bullets at your leisure, but it's that your test cables must be flight representative. If you're able to bring flight cables into an EMI test, that's wonderful. That's ideal. I've almost never seen that happen. For a lot of obvious reasons. Namely, it was handling, right? When you build the flight cables, you want to install them on the spacecraft with minimal wear and tear for a test campaign. So you're almost always building another set of cables for testing. But those must be built to simulate the flight cables. And if you can get the lengths to be the same as flight, so much the better. That's not always practical. You might not know the flight lengths by the time you're building test cables, but the real important part is the cross section. If you look at the cross section of your flight cable, so that's kind of what the second and third bullets are about, as far as twisting and internal shielding, and in particular shield terminations. You should be using connectors and back shells and shield terminations that are representative of what you're going to do in flight. And you definitely shouldn't be using test cables that are better than the cables you're intending to use for flight, because there you could mask a problem that can bite you on the platform, and that's one of the worst things you can do, right? You're defeating the purpose of a unit level test. So again, I get this all the time. Well, less so recently, thank goodness. But I used to get, it's the cables, not my box, and therefore not my problem. Again, wrong, wrong, wrong with capital R's. Call people out when they say this, because it is absolutely incorrect. So as an equipment provider, you are responsible for emissions that your box induces on all cables connected to it, and susceptibilities in your box due to energy brought in through the cables connected to it. So that this notion that it's a cable problem so it's not my box and it's not my problem, don't let people get away with that. That is completely incorrect. And you're responsible for showing up for your EMI test with proper test cables. So just a few more words here. Individual leads shall be grouped into cables in the same manner as the actual installation. So here again, this is the original diagram from the mill standard, and just note that where it calls out LISNs in GEVs, we replace that with a capacitor network. So if a cable is longer than 10 meters, at least 10 meters shall be included. And where cable lengths are not specified for the installation, cables shall satisfy these conditions. At least the first 2 meters of each interconnecting cable shall be run parallel to the front boundary of the setup. Individual cables separated by 2 keep saying 2 meters, 2 centimeters. Cable closest to the front boundary 10 centimeters from the front edge of the ground plane. All cables shall be supported 5 centimeters above the ground plane. And the question comes up about the 5 centimeters. It doesn't really explicitly explain that in the mill standard, but just talking to colleagues over the years and just kind of my own thoughts on that. If you know that you're going to route cables directly on structure on the platform, I mean, that's great. That's the ideal thing. But you don't necessarily know when you get to the final installation that you're going to be able to do that for the entire length of the run. Inevitably, you're going to have to run a cable around a corner or up onto a connector bracket on a panel that folds out or something like this. There may be some stretch where you're not going to actually be able to run the cable directly adjacent to structure. So when we do the test this way when the cables are 5 centimeters above the ground plane, it gives you an opportunity to characterize the emissions and susceptibility where the contribution of the ground plane is minimized. So like if you do a radiated emissions measurement, you're getting more of like, what is the cable going to emit when I don't have a significant benefit of the ground plane? You can certainly do a follow-up measurement where you look, if you're having emissions problems, and then do a follow-up measurement where you put the cables all the way down on the ground plane and see how much better that makes things, so that you can make an assessment of what is it likely to look like in the flight configuration. It's more than likely going to be kind of between those two measurements, right? But that's kind of the engineering, my best engineering explanation for the 5 centimeters above the ground plane. But the broader answer is that going back to the standardized test methods and credibility when you share results with other organizations, this is one of the big things to make sure you get right. Because if somebody is reviewing your test report and you completely blew off all of these guidelines, then all bets are off, and they're really going to scrutinize your test report and find all kinds of other things you didn't do right. So this is one of the things that really constitutes, how to follow a standardized test method and ensure that you have credibility and that you know what you're doing, right? Because when you hand somebody a test report and this is one of the litmus tests, right? If they see that you blew off all of these guidelines, then they're going to give you the reviewer equivalent of a colonoscopy. And that's not that much of an exaggeration, right? I don't think anybody wants to volunteer for a colonoscopy. Just get it right. Do the test properly, and you get by these initial litmus tests where if somebody sees that, okay, they set this up right. I'm still going to look at the rest of the test report, but they're going to look maybe with a little more friendly eyes and just see what you did, as opposed to trying to find out what else you did wrong. Okay. Uh, Actually coming up near the finish line, so we have to be, because it's coming up on 11 o'clock. So, okay, the mill standard specifies a peak detector for all emissions and susceptibility measurements. I think it's mostly applicable to emission, but it may not affect the measured value of a stable signal very much, but it will affect your measured noise floor. And that's what we're going to talk about here. In my test and measurement session, I go into a little more detail on this, but I'll show you some of it here. But thermal noise, if you just look at the noise floor of your measurement device, this is just one of our FFT receivers. Noise is random-ish. I mean, it's kind of random, but not really, right? It's a random-ish distribution around an RMS value. So you draw a line through the middle of this, that'll basically be your RMS, but then you see that you have peak levels, peaking up on top of this. So thermal noise follows a Gaussian or normal probability distribution. And I know I've been called, and I've reveled in the term masochist, but I will tell you now, I have always hated probability and statistics, and my brain has always melted with discussions like this. So I feel you if you're saying, "Oh dear God, we're going to talk about statistics," but bear with me, because this is important stuff, and this will help you understand something that comes up all the time in test and measurement. And once you actually understand where it comes from, I think it will stick a little better. So just bear with me for a couple minutes while we plunge into some of this. But okay, the equation might make your brain melt, but I think everybody's familiar with the bell curve, which is basically what a Gaussian or normal distribution looks like around some mean value. Okay, so mean is our mu. We just use the Greek letter mu to mean mean, and sigma is our standard deviation. So, and we talk about sigma, right? Sigma values. So I think most people are familiar with these terms, but just relating it back to where they come from. So if you just take some sample set, so capital N is our number of samples, so x sub 1 through x sub n, the mean is pretty straightforward. Our mean mu is just the sum of all those values divided by the number of samples. Okay, so then we look at individual samples deviation from the mean is just the difference of that, just the difference of x sub n minus mu. Okay, so pretty straightforward. Then you take the square of that sample deviation, and you can simplify this if you and sometimes I've seen it simplified where you like that initial graph, right, is just kind of assuming that your mean is zero. Well, this is defining the deviation from the mean, right? But if you assume your mean is zero, it simplifies things, but I think this is the more general case, right? But you have each individual sample's deviation from the mean, then you square that deviation, then the variance, what they call sigma squared, is the mean of that deviation squared. Then your standard deviation, if you're calling this sigma squared, your standard deviation sigma is just the square root of all this. Well, so you're taking a deviation from the mean, squaring it, taking the mean of that, and then taking the square root of that. Well, that kind of sounds a bit like root mean square, doesn't it? So, and that is more or less what it is. And so for thermal noise, this sigma value is what we define to be the RMS value of our noise. And in my test and measurement section, I relate that to this KTBR, but let that be a discussion for another day. So if we look at our graph of this equation for f of x, our probability distribution for a normal probability distribution based on this equation, the area under the curve gives the probability of occurrence in a given range of the deviation from the mean. Okay, so the integral is not possible in closed form. I've tried, surprise. And I talked to an old friend of mine who is a retired mathematician from a certain agency a little bit north of Goddard, whose name I'm not allowed to divulge. Well, I probably am, but anyway, I asked him, like, how do you do this? And he let me borrow his old statistics book. And basically they said, yeah, you can't do that in closed form. Just look up the numbers in the table in the back of the book. You have to take it numerically. So if you're a mathicist and want to try to do this in closed form, don't bother. But anyway, when you look at it numerically, look at the number tables in a stat book. When your deviation is less than 1 sigma, that's going to happen about 68% of the time. 2 sigma, about 95%. 3 sigma, 99.7%. Now we'll go to a log scale. It's the same graph, just on a log scale, so we can see things a little more clearly. If we go to deviation of being within 3.5 plus, where the absolute value of your deviation is 3.5 sigma, and don't worry, if your brain is melting, we're getting to the point here in seconds. When that deviation is within 3.5 sigma values, that's going to happen 99.96% of the time. So that means anything that's outside of that, anything that's greater than 3.5 sigma, is what I call not bloody likely. We'll call it NBL. It's just not very likely going to happen. You have to wait a very long time before you're going to get a sample value that's out there. So for all practical purposes, we can call that deviation from the mean, the peak value of that deviation from the mean, to be 3.5 sigma, approximately. So when we recall that we've defined sigma as the RMS, the root mean square of that distribution, that's actually at 1 sigma. It's not at 0. And that's a little weird. That's as much as I'm going to say about this right now. In the test and measurement session, we can talk about that some more. But for thermal noise, this 1 sigma is is our RMS value of our noise, of our noise value. So that means that the absolute value of the peak of our noise is going to be about 3.5 times the value of the RMS. The RMS is what tends to be defined in data sheets for measurement devices like spectrum analyzers and receivers. That's the significance of all this. And we convert 3.5 to dB, 20 times log of 3.5 is 11 dB. That is the crest factor for thermal noise that you will see quoted in textbooks or write-ups or even in some analyzer and receiver data sheets. So it means that the noise floor peak will be about 11 dB higher than the RMS value. So if you're trying to calculate what kind of dynamic range you have in a measurement system, and you take the specified RMS value of the noise or sometimes it's called displayed average noise level, DANL, in a data sheet. When you're doing mil standard 461 testing with a peak detector, you're going to have to add 11 dB to that value that they specify. This is something that's generally known for people who do test and measurement, and live and breathe it, but it's not widely instructed. So that's why I'm telling you this, why I'm spending some time on it. I mean, I had to dig through this and have people explain this to me as opposed to looking it up in a textbook. So if we go back to our diagram of noise here, our plot of noise, so here again, we can see that the peak value here is about 11 dB higher than the RMS value. And to just drive that point home, and that's our crest factor. So when you hear this 11 dB crest factor, that's what this means, that's what it comes from. So we take this same plot, this is just basically clear right, or a real-time plot. If you just let this run, you'll just see this kind of wiggle around, but with this general profile. But if you go to an RMS detector and just take a bunch of averages and just let it integrate an average, you will get this nice clean line. right? Which is basically right kind of through the middle of this distribution. This is where, when we say noise is random, and that's why we say yes and no. Like at any given time, you're going to get kind of a randomish distribution around the RMS value, but the RMS value is pretty much constant. I mean, you take the same measurement the next day, it might drift a little bit for thermal reasons, but it's basically going to give you a consistent result here. So where the marker is, just at 350 megahertz, we're at about minus 83 dBm, RMS detect and average. When we do things more in line with the mill standard with a peak detector, and when we put it on max hold, and so we let it integrate and just over time, you'll see it kind of level out to the maximum level. It's 11 dB higher, right? We went from minus 83 to a little above minus 72, so it's like 11.5 dB. But it's right in the ballpark of what the statistical prediction is. So that's the point here. That's why I thought it was worth spending a little time on this, because you can get a mistakenly optimistic assessment of your expected noise floor if you don't take this into account. The mill standard requires measurements with a peak detector, so it means your noise floor will be 11 dB higher than a specified RMS value that you might get from your receiver's data sheet. Okay, everybody with me? Does this make sense?
Yep, makes sense.
Okay. All right, we're almost there. Thanks for hanging on here. So for susceptibility testing, the mill standard specifies these scan rates and step sizes. We pretty much never do. I don't believe I've ever done analog scans. I mean, that's the way they used to be done, and for any old test labs with older equipment may still do things that way, but we pretty much always do things with stepped scans. Digital equipment will do things that, with stepped scans. So just taking a look at an example here, if we start at 1 megahertz, then the step size is 0.01 F naught. Well, what does that mean? It just means that your next frequency is 1.01 times your starting frequency of 1 megahertz, so it's 1.01 megahertz. Then your next frequency is just 1.01 times that, so it's just above 1.02 megahertz, and so on. And then in GEVs, we use the same step sizes for the first three ranges, but above a gigahertz, we provide a factor of 4 relaxation. We go from 0.25% of F naught to 1% of F naught. And generally that still provides sufficient coverage to assess susceptibility, but it with this step size, these are radiated susceptibility scans tended to take all eternity. Now they take about a quarter of an eternity. So a word about modulation. The standard modulation is specified as pulse modulation, 1 kilohertz, 50% duty cycle. So another bit of nomenclature, if you're not already familiar with it, just a straight up sinusoid in this jargon, or in this vernacular, not vernacular, but the terminology is continuous wave, or CW signal. Whenever you hear anybody say it's a CW signal, that's what it means. It's just a tone. It's a pure sinusoid. So modulation, compress the scale a bit here, but 1 kilohertz pulse modulation just means that the signal is on for 500 microseconds, off for 500 microseconds. And that's all it means, right? So you're with 50% duty cycle. So it's a total of a 1 millisecond period, on for half of it, off for half of it. So some implications for detector imaging systems. To first order, the noise is determined by taking statistics on pixel data. Now, different providers will use different techniques here, but I'm just saying to first order to get the point across. And so for a typical pixel period of 10 microseconds, so a sampling rate of 100 kilohertz, any frequency above the Nyquist rate of 50 kilohertz will be undersampled. And that's basically most of the radiated susceptibility frequency range. So the susceptibility at any given frequency will manifest itself as the total energy integrated over a pixel period. So you're going to have multiple cycles of your applied signal integrated over a 10 microsecond period. And so it's just going to be that total integrated value to give you the sampled pixel value. because when you go through an A to D converter, you're just going to get a number associated with the level in that pixel. Right. So at a susceptible frequency, an unmodulated or continuous wave CW signal will produce an approximately equally shifted signal in all pixels. So when you perform your statistics on such frames, it may show a shifted mean, but the standard deviation will not look much different from a frame where you were not applying the signal. So this can give you the worst possible result of a false pass. And we've had this happen, where we forgot to apply modulation, and we knew we should be seeing susceptibility because we had seen it before, and it was for those of you who remember Ike Orlowski, he was the one who was running some of these tests at the time, and he went back and looked at the mean from those plots and said, wait, the mean is shifted like on all of the pixels. Oh, we didn't apply modulation. We should do that. We went back and repeated the test, and boom, the susceptibility popped out like a sore thumb, like we knew it should. So the modulated RS signal will bring out the susceptibility where the CW signal is likely to mask it in this type of system. So you can see this herringbone pattern is very evident in the image. That's on the on part of the cycle. This more continuous part here, this more homogeneous area is on the off cycle. So that's more like what you would be getting if you just applied a CW signal, right? No, I'm sorry, I'm misspeaking. These parts are when you're switching from one frequency to another. But when the signal is on, I figure that's probably where the lines are a little bit darker. If you were not applying modulation, the entire frame would probably look like this, and you wouldn't see these distinctions here, and it would be less obvious that you had a problem. So in the image data, you clearly see this herringbone pattern, and when you take your statistics, it will be much more evident that you've got some variability in your signal level. Right? If your criteria is uniformity of signal, and you're just applying a CW signal and getting the same perturbation on every pixel, you're going to get a false indication that everything is okay. All right. Now, a counterexample is something like a pressure transducer, where it's just taking the pressure that it's measuring and it's giving you basically a DC potential as a function of the measured pressure. So when you an applied susceptibility signal will just ride on top of that. So if it's a modulated signal, then it's going to look something like this. And that might be a little bit hard to quantify your susceptibility, right? But if it's just a CW signal, because you know that shouldn't be there if it's a clean signal, right? So in this case, the CW signal actually might be easier to measure, easier to observe and quantify the perturbation to the expected level. And so in this case, if that's the case and that's your engineering assessment, you get to tailor the test method and specify a CW signal instead of modulation. I did this on a test. I mean, it's personal experience. I did this on a test on a pressure transducer a few years ago for that reason. When we were trying to look at a modulated signal, it got pretty cumbersome to try to determine how to quantify what the level of the susceptibility was. But when we just removed modulation and just looked at the CW signal, boom. Now we got the RMS value of that signal riding on top of our signal level and or the DC value, and then now we had like a very easy thing to measure and quantify what the level of our susceptibility was. So again, know thy EUT. Do your homework, talk to the equipment providers, understand how the thing operates. You don't need to get down to the level of being able to design and build the thing, but just know how the thing operates sufficiently so that you can do a meaningful test on it. So you want to be able to do the test to maximize your chance of finding a susceptibility if there is one. None of this stuff is cheating. It's But you want what it's the opposite, right? You don't want to cheat. You don't want to mask a problem because you didn't test it right. Like going back to the detector subsystem, we knew we should be seeing a susceptibility because we'd seen it before. And it was because we weren't applying modulation when we should have been. So you just know the EUT, get to know the equipment providers. They will almost always be very happy to tell you how the thing operates to make sure that you're getting a meaningful test out of it. The measurement system integrity check, mentioned this earlier, it's conceptually pretty straightforward. You apply a test signal into the whole signal chain, and what's not really shown here is when you go into to the measurement software that converts the directly measured quantity, which is generally a voltage or power, and then gets you back to current or electric field or what have you. There's generally some conversion factor in the software, but you want to apply a known test signal and make sure that you're getting out what you expect. And this is all part of just making sure you can have confidence in your test results. And don't skip this due to schedule pressure. Now, our EMI lab at Goddard, bless their hearts, they insist upon it. Like, nope, we're doing the measurement system integrity checks. We're just going to do them. So, but if you're in charge of a test, anywhere else, don't skip these measurement system integrity checks. They will save your butt later if anybody is calling, even if you yourself may be calling your test results into question. And all you have to go on is the report that you wrote a year earlier. And you say, okay, well, we did these measurement system integrity checks. I can have confidence that our results are valid. This is just the general setup in the mill standard, and this is showing the LISNs. And so the diagram in GEVS, it's all very similar, but just with the feed through capacitors instead of the LISNs. And now, about to wrap up here, we get back to our painter quiz. So does anybody have any guesses or insider knowledge as to who painted this picture and the age of the painter at the time? And you're probably wondering why I'm doing this, and I will tell you on the next slide, but go ahead.
Michelangelo.
Pablo
Van Gogh.
Picasso, age 14.
Van Gogh.
Who said that? Somebody has seen this before. Who said somebody gave the right answer.
Van Gogh.
Pablo Picasso.
It's Pablo Picasso, age 14.
Picasso.
So who said that? Did you know, or have you seen me give this before?
I reverse searched the image yesterday.
But who is that?
Isaac.
I'm sorry, where are you from?
The EML over at KSC.
Okay. What's your last name?
Davila Carrion.
Okay. Well, congratulations. I think you're the first person who has actually gotten it right. But yeah, I came across this painting at a museum. I think it was in Paris, because I think there's a Picasso museum in Paris. And I think I went through the wrong way. I didn't realize that, like, I went through his later works and was kind of going in the wrong direction. So I think this was the last painting I saw, and it was supposed to be the first. But when I saw this, and I'm not gonna like say that I have this lifelong passion for Picasso, but it's like, okay, there's a Picasso museum while I'm in Paris. What the hell, I'm gonna go. But when I saw this painting, I was really blown away, and it really helped bring a lot of things into focus for me, just in terms of his work, which is the very point that I'm making here. Because just imagine that if you're able to paint like this, if you're able to paint a stunning portrait like Rembrandt, if you're able to paint like Rembrandt when you're 14 years old, do you want to spend the rest of your life just painting portraits like Rembrandt? Probably not. You're going to go on to and spend the rest of your life doing your own thing. It's like, all right, I can do that. I know how to do that. And so I'm going to keep expanding my, I'm just going to keep pushing what I can do and do my own thing. So the point is, when you know the rules inside and out, when you can paint like Rembrandt when you're 14, that is when you can get creative with them. And you probably are still wondering why I'm bringing this up, but it's when you know what's in the mill standard and gives inside and out and can quote chapter and verse from it, that's when you can get creative with the rules and convince people that you know what you're doing when you're saying, well, okay, we're going to deviate a little bit from what's in the mill standard because this is a better fit for what we're trying to do. Excuse me, a better fit for what we're trying to do in this particular test. So when you know the rules inside and out and can quote chapter and verse to people, you got a lot more credibility when you're doing your tailoring as opposed to just doing it from the standpoint of, well, we're not even going to bother reading the document and we're going to just do it our own way. You know, that doesn't get you very far. At least
So,
what's that?
so what prize did he win for saying Picasso?
Yeah, so I actually meant this, a gold star maybe.
I'll take it.
All right. Well, no, well, whenever I can get down to KSC, I'll buy you a beer. So, or
Perfect.
some equivalent if you don't like beer. So,
Yeah, we'll figure it out.
yeah. All right. Well, and that brings me to my last slide. So the summary, well, read Gevs and Mill Standard 461. Again, don't like just open it and try to read it cover to cover in one sitting. That's kind of self-correcting because I don't think that's going to work real well. You'll get a few pages in and say I need a break from this, and that's fine. But just get familiar with it. I mean, that's how you get familiar with these documents is that you just glance at them on a regular basis, and eventually, and it's the real point is just knowing where to go. You know, I certainly don't have those things committed to memory, but I know where to go look. You know, and I can usually find what I'm looking for within a couple minutes when I go to look something up. And so we'll get on to detailed test methods in upcoming sessions. If I'm actually back from travel next week, I'm likely to be there into the weekend, assuming my approvals go through. I'm gonna check my email to see if that's true. But Monday's a holiday, so I'm probably move the Monday session to Tuesday. So we'll probably do Tuesday, Wednesday next week, and we'll get into conducted emissions. So that's all I have for today. Does anybody have any questions?
Good job, John.
Thank you, and you're welcome. Anybody have any specific questions before we adjourn?
I had one. I was going to email you about it though. It was regarding the conducted emissions transient domain testing. We have something coming up, and I was wondering what you guys do. We have a circuit we built, but just if you had any insight. But that's
sure. Phil, you can email me that. But yeah,
okay.
that's getting into some specifics.
Yeah.
That might justify a dedicated session on its own because
Nice.
the conducted emissions session I'm going to do next week is the standard frequency domain based tests, but the time domain stuff is important too, and it's different enough that I don't think I'm going to try to cram that in because the frequency domain stuff's pretty full, but sure, email me your question and then that may actually help me shape a session on that.
Awesome. Thank you. Will do.
Okay. Anybody else? By the way, who is that speaking? I'm sorry.
That was Isaac again.
Okay. So your email can be to claim your gold star in your beer.
Perfect. Yeah, I'll take it.
All right. Awesome. All right. Anybody else have any questions? All right. Well, excellent. Thank you for for showing up. Well, for those at Goddard on a snow day, but thanks for showing up. Thanks for the enthusiasm, and I'm going to keep letting my management know that people are getting something out of these. So, and it'll help me keep doing them. So, all right. Thanks very much. Have a good day.